It does it. Yes. Yeah. First of all, thank you for having me. It's great to be here. It's the first time actually I'm at IAIFI, the greatest machine learning physics place on Earth and in the known universe. I'm by the way, I'm the leader of the IAIFI fan club. So I'll talk a little bit about machine learning for LHC theory. As always, I start, even though I'm turned towards essentially doing machine learning my entire time in my midlife crisis years. I'm still motivated by the classic LHC paradigms, the question, what's dark matter? Can LHC tell us that if we have variability, and where does this Higgs field come from? Right? And why does it feel like it has to assume vacuum expectation value, which is these are things which are really important to our existence here and the universe, and we really don't know the answer. And particle physics might be able to eventually shed some light on those. And what's interesting when you do machine learning for particle physics, there's a couple of unique LHC opportunities that we have when we work with LHC data. The first one is, I know that our Cosmo friends don't like it when I say that, but we do have spectacular first principle simulations, and when I mean they're really helpful is they're so good that we can train networks on simulations and use them on data and find stuff that is just not just shortcomings of the simulations. We also have a ginormous data set, petabytes per second. Most of that our experimental colleagues throw away, but it comes in. And we have an amazing level of uncertainty control in the sense that LHC is probably the first hadron collider, precision hadron collider we ever managed to build. And then LHC has a glorious past. That's usually based on measuring event counts, and it led us to discover the Higgs discovery, even though that's not quite true. The Higgs discovery already involved a lot of methods which went way beyond counting events, including likelihood methods, and then lots of exclusions of new physics. And then because we have LHC people here, 63 or 64 discovered hadrons, which is spectacular discoveries, and you should not blame those hadrons on these discoveries on us not feeling too stimulated by them. Really, it's a spectacular outcome. We don't talk about this enough. We always say we don't discover anything at the LHC, and that is not true. It's just we don't discover anything at the LHC that Tilman Plehn cares about. And this is I apologize for that. It's nothing bad about it. It's about me. And I'm a theorist, so what we do is first principle simulations. We start with the Lagrangian, and then we use quantum field theory, and then we eventually put in detectors. And for all of that, we heard this in the earlier talk, symmetries are basically the governing principle. And we start discussing symmetries in theoretical physics 1 and 2, when we use Noether's theorem in particle physics, and we never stop talking about symmetries. And with the help of the simulation chain, we generate something that I like to call LHC collisions in the virtual world. In the virtual world, that's described by a Lagrangian and a real detector. And then we do inference with that. And if you have these simulations and you have huge amounts of data, it's very, very clear. The answer to this model inference is a simulation-based inference. And we heard beautiful talks about this morning. So it's not just LHC that's looking at the simulation-based inference. And what's important to me is simulation-based inference will allow us eventually at the Heidelberg velocity LHC to understand all of the LHC data in terms of first principle theory, quantum field theory. And that is a spectacular achievement. Of course, it would be even more spectacular if you could also discover BSM physics. And if there is BSM physics to discover, these methods guarantee us, because they're optimal, that we actually discover it. However, who knows? It's BSM physics, we don't know where it is. If it's there, we'll discover it. If it's not, we will understand this enormous amount of data in terms of first principle and fundamental quantum field theory. Now, when you look at this kind of package here, you see that's an obvious ML case, right? Machine learning you can use for so many things here. And this is for instance, my simulation chain, just in my favorite little plot here. There's a fundamental mistake here, if you spot it, let me know. So this is we can't compute scattering, decay, QCD radiation, shower, fragmentation detectors, and then the events. So what's the role of theory in that game? Well, theory is, no, this isn't pompous, but I like it. So we turn data into knowledge, like the theorists, actually with the help of the experimentalists. I admit that. So, and the basis of all this quantum field theory, and start with Lagrangian, then if you have ever one in these event generators, you generate Feynman diagrams Then you compute the hard scattering to like any loop order in QCD that you're able to do that. You compute decays, you compute jet radiations, and we just use actually machine learning where you describe the role of partons inside protons, hadron level QCD, which is, by the way, one of the biggest challenges, and not enough people are working on that. And then we end up with these like first principle simulation of events. And there's a language problem here because, I always said this is first principle simulation, is not modeling. And then my machine learning friends say, but modeling is all first principle simulation. So let's just fix the first principles, like complete theory, like range, and then we go. Right? I'm not interested in modeling TD bar events and saying a machine learning network can describe TD and generate TD bar events. Obviously, it can do that. It's just I learned nothing from that. Okay. Why are we currently a little bit challenged? And that's because the IAIFI, which will generate about 20 times more data compared to 1.2. That's like the last one that we completed analyzing. This is a statistical improvement of root 20, and that's bad because this is the kind of the level of precision you need to reach. So we basically need to learn, and we heard this from Aya today already, the rate of our phase space to per mil or something like that. Like, our phase space is like scattering phase space, just outflying particles, like energy momentum. And why does that affect theory? Because simulation-based inference starts with simulation, and simulations at the LHC is a theory job to do. So this is what we have to do now. And speed is the key. By the way, speed is the key. And there we are lucky at the LHC in the sense that you can also exchange speed for precision, and not just for like numerical precision, but if you're very, very fast, you can actually go to higher orders in quantum chromodynamics and QCD calculations. Like the reason why we don't include true loop calculations systematically is not because they are also super hard, but there's a lot of smart people who are doing them. So we mostly don't include them because they're too slow in their implementation, numerical implementation. So what we then do is we take our simulation chain. We want to improve this module-wise, and this is like what I'm working on, like in my day job. It's called Madness, math graph, neural important sampling, and like Sherpa, doing similar things. So we're trying to make this better. By the way, this is a way that's something we just put into a NeurIPS paper. So this is how people from data science industry envision how as cheap as this goes. I like the idea that here on the right-hand side, you get a discovery and a Nobel Prize for discoveries and measurements. That's the last time I checked, okay, the measurements and Nobel Prize, and that would be nice. Okay. And what role does generative AI play here? Well, this is like my group, like working on like a forward simulation. So like we generate stuff, and it's very clear that like when you generate stuff for the LHC, that you want to use like generative networks, especially now that like the generative AI kind of revolution is happening right now, and then every year you have like a new cool tool that you can play with, and that improves actually your standing in a situation significantly. So at the end of the day, what we always want to do is we want to learn a phase-space density, and then we sample from, for instance, in Washington, that density, and this is how it goes. Well, this is really in a nutshell what we always do. And then when we started doing this, the variation autoencoder phase was already over. So I got in late. So we started with GANs. So like there are still probably, in my opinion, the coolest generative networks because of like the game theory aspect of them. The problem is that they're not super precise because if you have two players playing against each other, like the two of them have to form a compromise, and that compromise might just be crap. But they are both happy. And like how do you push them to say like so you need like at least a referee to say like your compromise is not very good. So it turns out well, for our number of dimensions, often normalizing flows or now modern diffusion models are actually especially useful to model stuff. With one exception, and that is actually that brings me to the last talk that you heard about like geometric deep learning. With one exception, and that is if you think about phase space. But phase space looks very complicated, like on-shell particles, intermediate poles, and stuff like that happening. But when you put in Minkowski metric or like Lorentz invariance, you notice that phase space is actually not that complicated. It's very local, and everything that we try to describe at the LHC in terms of phase space is a single model. It's not very complicated. It's not a very complicated function. The point where complications do come in is combinatorics, when you have to assign things, because then all of a sudden things do get multimodal, right? And this is the point where we, like, for instance, use transformer structures here. JetGPT is like something we did for the event generation, or like vision transformers for detector simulations. So what we typically do is we, like, nowadays we combine normalizing flows and JetGPT, and the latest, like, great piece of progress that I made the first time working with Jesse and a bunch of Qualcomm AI geometric deep learning guys, like Tilman Plehn and Johan Bremer. We are building some networks which guarantee Lorentz symmetry, which makes it so much easier. And I'm just, like, advertising this little plot here. This is the number of training samples for one of the, like, TT bar, just event generation. And this is the AUC. It's just, like, a measure of quality, not a particularly good one, but it shows what we're doing here. And you see that, like, this is a regular, like, generative network here. And let me, like, have a classifier that we compare how good this generative set is compared to the training data. And this is 0.8 here in any case, and here you go to 0.5, and you drop very fast. The models that we use, by the way, to improve things, aside from this Gator architecture, is combinations of transformers or attention layers mostly, and flow and diffusion models, to be specifically CFMs. So what we can do, there's two things. You can either, like, take a CFM and put attention layers in to, like, take care of the combinatorics, or you take like, some kind of, like, a transformer architecture and put little CFMs in there to, like, map out your structures, and we use one of them is transformer and the other one is track FM. Yeah, and then we take all of these, like, different models, and we try to see, like, which of these modules we can improve. Like, for instance, the vision transformer, I think, is currently the leading contender here. Like, and these others, like, the track FM here, you will see it's actually when you go from here to here. Fragmentation is the big unsolved problem, and so on and so forth. But QCD radiation is hard because it doesn't have a well-defined number of outgoing particles, so that's probably a point where you want a transformer to generate events. Anyway, so we pick and choose and do this module-wise, and then we improve things. And when we improve things, we need to measure. Like, I need to be able, and, like, I already, like, alluded to this earlier. If I want to improve things, I have to, like, basically have a clear statement. I'm a better or worse than I was before. And so that, like, in particle physics, what has become, like, I think the most powerful metric to decide if a generative network is good or not is just run a classifier. You run a classifier over the same number of generated events in your training events, and you see can tell them apart. And if yes, then you actually have a classifier weight here. This is like, thanks to Jesse and Ben, this is, like, the standard, like, doctoring or, like, reweighting or however, like, whatever you want to call this strategy. But, like, you can improve your simulations, and if you're close to 1, then you know how good you are. And then you get these kind of distribution. These are the event weights. This is 1, and this is, for instance, like, one of the tasks that we recently published. And what's nice is that, like, depending on the weights here, like, where you actually see tails, you can even in phase space, you can identify failure modes, like, for instance, missing features, which lead to, like, tails here, or, like, missing cuts, which lead to tails here, stuff, like, that need to be corrected. So this is what we're typically looking at, and what I want to point out here, so this is, like, 5 orders of magnitude from here to here, and this is 10%. So we're pretty good. However, what I just told you about is madness and, like, generating stuff, and it's hard work, and it's like, you make an improvement here of a factor 2, and you make improvement there of a factor 2, and that's the, like, everyday life of, for instance, an LHC experimentalist, right? I mean, like, you're happy you make a factor 2 improvement here and there, and then, like, at the end of the day, like, in Heidelberg, my friend, the, like, former vice president of the university comes and says, like, okay, what's really changing in particle physics? Like, and I said, like, we're making progress factor 2, and he said, like, not interested. So, like, what do you say? Like, where we do transform LHC physics? Like, how can we use machine learning to do something that we couldn't do before? Or, to be more precise, somebody will always say, I could do this before, but let's say something that we're really bad at before, right? And that is unfolding. And let me just motivate unfolding. So unfolding basically means that I want to use, like, simulations not forward but inverse, and I want to publish data not only at the, like, at the analysis level, but, for instance, like, at intermediate levels here For instance, a bunch of events, like 100,000 TT bar events, how do they look after the shower, but before fragmentation? I can do that, right? Technically, I'll show you in a second how that goes. Why would I want to do this? Well, first of all, when you do simulation-based inference, you have to run simulations for every signal, right, that you want to check, and very carefully. And you also have to calculate these, like, predictions for every signal with very high precision to high power and QCD. But now you need to remember that the model builders who come up with models don't believe in their own models, like for as long as it takes you to do the like two-loop calculations. So there's no point in doing this. So in other words, what we want is we want people to like, check their models themselves. Like, why should I actually spend my time to check your model? If you like, I can give you data and then you check your model. And you see it's good or bad, or is it better than the standard model? But for that one, I need to publish that data. The other thing is theory limitations are crucial, like limitations currently for a lot of LHC analyses. Like Higgs analyses are theory limited all over the place. TT bar is theory limited all over the place, and progress is happening. Do we really want to rerun every analysis once a new like higher loop calculation for TT bar production comes out? Well, it's a pain in the ass. You don't want to do this. You want to publish the data and you want to tell people, look, you can check your new calculation with this published data and tell us how it looks. Yeah. And the last one is, there's this common law that LHC data is way too complicated for amateurs, right? And that is actually true. Jesse can tell you something about this. He tried, and he is the only person who actually ever succeeded to work with CMS open data, I think. But that might be related to the fact that he has a CMS group here. I never managed. So, like, it is too complicated for amateurs. However, I don't give what's the word? about detectors and fragmentation, because nothing that happens in detectors or fragmentation from a fundamental physics perspective interests me. So, like, I want to analyze this data, and if LHC experiments would actually unfold to here, I can do that simulation easily. As a matter of fact, we're writing it, so yes, I can do that, right? So I want to publish the data here. And by the way, if somebody wants the data here, like for instance for an EFT analysis, I also want to publish the data here, right? So I want to unfold from here to here, and from here to here, and from here to here. And how do I do this? And now by this, this is something that you cannot do right now. So how this is look like, mathematically? It's actually very simple. You have some phase space distribution in the Vico phase space here, data versus simulated, and forward inference compares here, right? You also, in principle, have at the parton or particle level, like read this however you want. You have simulations here. The forward simulation is described by this condition probability here. That's just the forward simulation of the detector. Think of the forward detector simulation here. And if you could invert that simulation here, inversion just means like write down this other way around for condition probability. You can define this unfolded probability, and you can do an inference here. And mathematically, that's totally clear that you can do this. And these two condition probabilities are unfortunately related with this extra factor, which means if you pretend one of them doesn't have a bias, the other one does have a bias. Right? You can't just like, they're not just same or inverse or whatever you want to do that. With this space theorem, you don't get around that. Now, if you assume that everything is stochastic and you're not systematically losing a lot of like information, this problem is totally symmetric. It doesn't matter if you do it like, describe everything here or here. So if you go down here or up here, same information. You actually learn from the same paired events. You will learn this, like, the simulation from the same paired events. You can do this, can learn this for conditional probability or that conditional probability. So if that is true, then we know that we can use machine learning for unbilled and high dimensional unfolding. Or actually, we have high hopes that we can, let's say. Or we had high hopes until the first people showed it. And let me give some credit here. So this is Jesse, this is Ben. And these are the people who kind of founded IAIFI. Is that correct? So like, these like, the three guys here, they are the young stars who basically just jump started everything. Incredibly smart. It's such a pity that they left and are no rich. And what these guys, Jesse and friends, say like, I can learn a mapping here between those two things, right? So I just recopied that here. So I can learn classifier weights from here to here. I can pull and push the weights up, down, up and down here, and then can use those weights after a self-consistency check to generate this unfolded distribution by reweighting that simulated distribution. There's one extra step I'm skipping here, but like, this is really the idea. So what they do is they take this little square and they basically evaluate all three directions except for that I care about. and they like go from here to here to here, and of course they arrive in the right spot. And that works. There's a beautiful paper, Z plus Z in 24 dimensions, I believe, unfolded in Atlas right now. You can talk about the networks and why anybody wants to, like, train tens of thousands of network networks or something for that. So what I'm saying is a huge pain in the ass to do, but it was recently delivered, and it's a beautiful piece of work. And that was driven by the now established ML classification progress. That is the same kind of machine learning progress that's driving jet tagging, which basically has destroyed everything non-machine learning in the field of jet tagging, as we also heard this morning. No, Matt mentioned that. So my favorite unfolding method is slightly different. I mean, it targets the same problem, but I just want to directly just learn this conditional probability. And since I know as a forward simulation person how I can, like, learn this forward simulation probability, I can also know how to learn this one, right? Yeah. Historically, the reason why we are not actually, like, in playing this, like, level playing field like right now with Omnifold is for three reasons. First of all, we used the GAN before the first, and it doesn't work, so we had to switch networks to actually get a probabilistic interpretation here. Our networks still were not precise enough, so then we had to change networks again, and then we have to remap the training prior, which is some work that Anja Butter and Monica Danforth and Matthias Backes worked on. Any case, and this machine learning project now is driven by generative AI, not by classification. And generative AI, we all know, started after classification. Okay, however, we can do that now. And I'm going to show you some results that were very played with this. And this is, like, thank you to my friend Roman Kugler, who said, look, we have done unfolding. So, like, as I said, people have done unfolding. Roman has done unfolding. And he measures top decays, hadronic top decays, and, like, he looks he checks how they look, and he basically, like, prunes them, and he gets these three subjects, and then he measures the top mass in the unfolded version, and then he also, like, wants to unfold the data altogether in the full kinematics, so people can check for new physics effects. So now this has been done, however, in a very, very simple manner. I don't have plots here, but, like, in a very simple manner, like, for instance, 5 bins in, like, in MT. So what's happening here is, and now we have to be a little bit careful, that this top mass, basically, when you ask machine learning people, they will immediately tell you, gives you an absolutely horrible bias or model dependence. So let me just mark these blue here, and let me just walk you through the different top masses that enter here. So in the forward simulation, right, your data that you have simulated has a simulated top mass measurement mass value here. Since you want to measure the top mass, this is just a guess. It's a number you put into your simulations. Yeah, you hope it's good. The forward simulation, by the way, here, like the detector forward simulation, doesn't know anything about the top mass, doesn't care about it. However, that data does. Now, here, in the real data, the real data, of course, doesn't know anything from the, like, about the Plehn setting that you chose to describe the data. So this is the real data top mass. However, because you train your inverse simulations on this here, on this data set here, the inverse probability adds the biased top mass, and so your unfolded data is both, like, true top mass from here and the biased top mass from here. And when you now look at, like, the structure of this problem, it gets horrible when you notice that, as a matter of fact, when you look at what's happening, is you get a complete training bias in that when you actually do it, the unfolded data knows absolutely nothing about the real top mass. It basically just memorizes the top mass that you put in here because it's such a dominant feature. So if you want to solve this, you have to, like, be a little bit creative. And, like, Roman came to us because he said, Omnifold is not going to do this. We don't think it's going to do it because the unweighting in the top mass, because it's a mass peak, it's ginormous factors, and it's very, very hard to converge. So what we decided when we want to do this, I mean, in principle, it should work. However, we need to work on our model such that, on the one hand, we weaken this bias here. You weaken the bias essentially by giving the network no training data with 5 different top masses, and don't tell it which one it is, right? Like, just a bunch of them. And the second thing is you give this piece of information to the data, for instance, as a batch-wise average, like, and then it knows more. So, like, you strengthen dependence on that here, you weaken the dependence on that one here from the training, and then it turns out it works magically. So, like, what we now did, and we're using, like, quite advanced machine learning tools. So we're using like, nice CFM models with transformers and like self-attention layers in the CFM in the flow matching. And what we see here is one of like our preliminary results. This is a triple jet mass that should come out as the top mass. And you see the generated data. So this is CMS generated data in black and our unfolded data in red. And the red line here is the relative deviation here. This is like, we're even around the peak. Like, we do have a slight broadening of the peak, but we're talking about 5%. The before unfolding, we start from this blue one. So that's way off. So like we have actually resurrected that mass peak. We have also resurrected, and that's actually no experimentalists come in and said, like, I was happy to see that, but then I said, yeah, no, but we also need the W mass because we need to calibrate. So you go back, you do the W mass, and you see, oh, okay, lucky day. W mass also comes out right, so we can even calibrate this thing and see it, right? So now we can actually show that these things can be under the top decays can be unfolded. And then this is just one of the many, like, then you can do a 12-dimensional unfolding. The data that we eventually want to publish, and then you get all kinds of like correlations. And I don't even want to go into them. You get a million, and they all look the same. Like they all look good. As a matter of fact, to the like and since I didn't tell you what our representation of the phase space is, I mean, these things are already correlations. I mean, like choosing phase space directions smartly is one of the things. So we'll try this on CMS data next, or actually not we, actually Roman Kukla and his group are going to try this in CMS data next. But we are very confident it'll work because we know it works on their simulations. Okay, so that's one of the ways you can actually transform LHC physics. But if Roman said this transformative because he did the unfolding before, and now he does the unfolding with machine learning, it's a very big difference. In the documentation here, it says Tilman like Bayesian networks. So I felt like I want to at least mention Bayesian networks. Yes, I do love Bayesian networks. Actually, I love uncertainties. And there's one thing that I like, two things I want to show you very briefly. One thing here is generative Bayesian networks, and like we started working with them with Manuel Hausmann, who's a machine learning guy in Heidelberg, or was now, he's currently in Denmark. And what we basically looked at is here, like, normal density estimation, two-dimensional ramp or something, and then the uncertainty it learns. And what we liked at the time here is that the uncertainty, like, has a structure. And that tells you something that, like, your network actually doesn't just, like, sample-wise, like, patch-wise learn densities, but it approximates a function, and the uncertainty on this approximation has a minimum here in the middle, roughly. It's simple why that is. Well, at the middle means you have correlations from all sides that you can evaluate, and so you get the best uncertainty here. We then like went and applied this to like LHC event generation, and like we can basically like do this kind of, this is the Z plus Jets PT of the leading muon here, and like this is like our training data on our reweighted prediction, and like what you're supposed to take away from here is that it's almost the same, and the like reweighting function is super close to 1. Now, if you look at it closer, you see that it's not quite at 1, but the gray arrow bar here is the Bayesian network. So that deviation from here to here can be explained by a statistical uncertainty in the training data, which in turn is described by the Bayesian network. And then there's another thing that we played, and that's systematic uncertainty. So we shifted PT of the jets a little bit systematically by like, some like, number here, and then we sampled through a conditional generator, and we can even describe that. But this is not what I wanted to show you. I already showed you like CMS simulations that I was not allowed to show you. And as a theorist, I want to be a fair person. So let me also show you some Atlas things I'm not allowed to show you. So this is calibration. And I'm working with this with my friend Peter Loch. And we had too much beer and discussions about machine learning. Peter is a year from retirement, and like and so like he wanted to see machine learning calibration work. And let me just show you the result. So we have a calorimeter that I know absolutely nothing about, absolutely nothing, like but I can still calibrate it because I have a friend who knows a lot about calorimeters. That's Peter Loch. And so what we want to learn is the calibration of the electromagnetic calorimeters for topo cluster output here. What you see over like the positive. And then we use our Bayesian networks. I promise I do this, like, actually, by the way, Nathan talked about those as well. And I want to do this with uncertainties. And here's like two things I want to show you. First of all, it's the first time that we look at the pull distribution. The pull distribution is the deviation of the spread of the data normalized by they learn uncertainty topocluster by topocluster. That is the histogram that comes out. This is, I mean, not a perfect Gaussian with plus minus one, but it's a pretty nice function called Gaussian-like shape with plus minus one. So we can certainly say that our uncertainties do describe the variation of the data of this specific this specific problem of the collimator. Okay, now I can do this, but is it any useful? Well, what we then looked at just for fun, we looked at the uncertainty and then we found this kind of structure. And we found, well, this is all screwed up, right? I mean, something funny is happening here. Some of our topoclusters stink. Actually, no, our calibration of the topoclusters stink because, you know, here, look at this. Again, you get a secondary peak in the uncertainty. And we like, you know, try to solve this with machine learning for a very long time until our perimeter expert friend Peter said, why don't we just look at these things and see what they are? And then we looked at them. And then we noticed that indeed the coverage of the calorimeter and atlas is not perfect, and there are little holes in there. And all of the, like, you know, uncertain calibration topoclusters that we found, you see a bit modulo 1, 2, and modulo 3. You know, they all sit here. And if that's not explainable AI, I don't know what's explainable AI. Like, you know, I can tell you from our like, calibration function where the holes in the atlas calorimeter are. So, like, you know, I know something about the atlas calorimeter. Okay, I'm supposed to be done. Oh yeah, I'm changed color. Okay, so now here's like two lines I can give, like, you know, depending on, like, you know, what the audience and how concerned the audience is. So one line I give to my make about machine learning is that it's just another numerical tool for numerical fields. This is the way I get out of trouble, right? I mean, then all the people over 60 in the audience who don't shout at you, then throw stuff and so on and so forth. So that's good. However, it's not true. What it is actually a new language that transforms the way we do science, like Matt Schwartz said. You know, so that's, you know, like with this audience, I can be honest, right? And since it is not going to be on YouTube, okay, yeah. So I can say that here. It's a new common language, and it, like, you know, opens all possibilities, right? And this is like what Matt Schwartz illustrated so nicely in his first talk. And even better, it's for free because somebody else is paying for it, so not us. It's like, you know, it's paying data science, medical research, like, you know, everybody's like, you know, paying money to, like, you know, allow us to do these things. So now we're going to have these thousands, actually I thought it was 10,000, 1,000 Einsteins, and that's you. And they will improve established tools. Okay, fine, like, you know, for a while, until, like, you know, the machines do this all themselves. You can actually develop new tools for established tasks, or you can just like transform through totally new ideas. And I just want to say, like, you know, all the young people in the audience, you're the, like, you know, golden generation, right? I mean, I'm the kind of guy you calculated next to, you know, like corrections to SUSY cross-sections to stuff that doesn't exist and so on and so forth. And I mean, Atlas and CMS have still not noticed that they don't exist, so there is no progress, right? SUSY is just getting heavier. Whereas, like, you know, when you do machine learning, I'm not kidding you. When you do machine learning in, like, you know, any field that you're working with, and, like, you know, here I'm like basically like connected to Nathan's, like, you know, good advice from old guy to young people. It's like you're the younger generation. You can generate progress at a rate that, like, you know, scares everybody over 50. And, like, please do that. Okay, thank you. Questions?
So for your top mass unfolding,
yeah,
you took you decided to kind of condition your unfolding on one variable and then produce 12 variables or even more variables as a final state. What's to say that the other, you know, invisible variables that we're just assuming are not, you have to condition on those, right?
You mean in this explicit,
right,
you know,
so for example, you
here.
condition on top mass, but, you know, what if there's some, you know, spin correlations in the top decays that, you know, the Monte Carlo is assuming, but the data is doing something different?
Then I will get a wrong result.
Yeah.
Yeah.
So is there a strategy for you to kind of arbitrarily apply this condition on as many variables as you can?
Yes, it is. And this is actually so in Omnifold, there are these iterations which do exactly that. So, like, you know, they make sure that your multidimensional distributions agree between your, like, you know, assumed simulations and the data. And here in our case, this, it's called the ICINN method, like, you know, by Anya and Monica and Bogdan. That should do that. So like, you know, right now, we're not employing these extra steps because we have checked that we wouldn't need them. However, Roman will do that. So we have to, like, you know, go through the same iterative methods that Omnifold goes through. And really the same way, if you think about it. However, the problem is, if you're way off, like in the top mass, that algorithm is not going to converge. And also remember that it costs you data. So like if you have many iterations, you lose statistics. And if you want to measure the top mass, you don't want to lose statistics. So this is basically, think of this as a pre-processing to enable the standard method.
Yeah, okay. I mean, yeah, I could ask more, but yeah, that's fine.
But it's what we're using is exactly the same. So
Yeah,
I think Ben will argue that it's exactly the same as the iteration here, the ICINN and the Omnifold method.
I mean, you know, the point being is it's never obvious when you stop, right? Because there's always hidden variables, right?
It is true.
Yeah. Anyway.
If you it's not totally obvious when you stop. Yes, right. But it is obvious when you stop, and that is, you know what the statistical uncertainty is when you go under the statistical uncertainty.
But then you have to define, you know, uncertainty in a like arbitrary dimensional space, right?
Yeah.
Which is not obvious either, right? So
for that you will need to bin, yeah.
Yeah, and binning an infinite number of dimensions is impossible, right? So
yeah.
Anyway, we could argue about this.
We could argue about that. I like to argue about this. Maybe we'll have to go back to that, to the classic paradox.
Okay. Yeah, that's all I have.
But it would be interesting to talk about it. I mean,
more questions. Thanks, Tilman. The most impressive thing that you showed was that you got Peter Locke to care about machine learning. I never thought it was ever going to happen. You know, we're friends, and even though we're friends, we can still talk to each other, despite the fact that apparently you don't like fragmentation. You want to get rid of fragmentation. And I think from the theory perspective, fragmentation is the aspect of the theory pipeline which we know the least about.
Yeah.
Because it's non-perturbative. And you know, you said it's all first principles, but unfortunately that little asterisk on fragmentation kind of hurts. So I'm curious what you view the kind of the role of machine learning, even the role of theory in that step of the chain, which I agree for certain BSM scenarios is kind of irrelevant, and that aspect of modeling is not that important. But if we're really imagining 20 times more data high level on LHC, and you really want to get, you know, the level of precision that the theorists should promise our experimental friends, we have to do something about fragmentation. I'm just curious what your vision of that is.
My vision of fragmentation. You're asking the right person. What? Okay, that's one thing. It's actually quite ironic. I once looked into like at least the hadron decays and stuff like that a while ago, because I want to know, like, you know, and thought about uncertainties and how do you include uncertainties, because in the standard, like, you know, packages, there's no uncertainties. And we published this as part of, like, you know, some Cosmo thing, like in Herwig for dark matter, because for light dark matter problem searches, you have exactly the same problem, right? Like, you know, when you look for, like, you know, light dark indirect detection of hadronically decaying light stuff, right? Same problem. So first of all, I would hope that at some point, like, you know, we get a better treatment of uncertainties, which is something that just needs to be done. And it's probably a lot of work, but it can be done. So, like, you know, propagate the uncertainties from the measurements that enter your, like, you know, hadron models into the output. And I know the people who wrote these packages, and they're excellent scientists. So my best guess is for the current precision, it really doesn't matter, because that's, like, you know, what they thought about. But I totally agree with you. 20 times the amount of data, we might have to reconsider that. And the other thing is, I can already, like, say, like, you know, let's, like, talk to our Cincinnati friends and, like, you know, help them as much as we can to sort this out. I mean, there are people who have ideas, and their ideas are very good. If anybody, like, you know, wants to write a differentiable hadronization package for Pythia, like, you know, that's probably what we need. And it's probably also the solution, or maybe not. I don't know, but I totally agree with you. It needs to be sorted. And more people need to work on that, because you know, wouldn't it be sad that, like, you know, instead, like, unfortunately, they achieved, like, you know, we couldn't really discover any new physics because we, like, didn't have a hadronization package that was good enough. That's just not so nice.
More questions?
Last chance. All right, let's thank Tilman again.